In section 5.6, we're going to look at properties of linear relations. So let's take a look at this relationship. It's the number of extra toppings for a pizza and the cost. So for 0 extra toppings, the pizza costs $12. And then for 1 extra topping, it's $12.75. For 2 toppings, it's $13.50. For 3 toppings, it's $14.25. And you notice that my domain, which is the number of toppings, there's a constant change of +1. And for my cost, which is my range value, there's a constant change of 75 cents. So there's a constant change in the domain and there's a constant change in the range. And that is why I get a graph that, if I was to join those dots, it'd be a linear function. But again, we wouldn't join this graph because you can't get a half of extra topping or 1.5 extra toppings, they're whole toppings. So this graph would be plotted as separate points. For a linear relation, a constant change in the independent variable results in a constant change in the dependent variable. So again, we saw this here in our previous table. Okay, which of these tables represent a linear relation? Justify your answer. Well, if we look at our Celsius Fahrenheit chart here, in my Celsius column, I have a rate of change that's constant, it's +5. And in the Fahrenheit column, I have a rate of change that is +9. So this one here would represent a linear relation. The relation between current, which is measured in amperes, and power, which is measured in watts. Here I have a constant change in the amperage of +5, but the power is not a constant change because it's 75, then it's 225, then it's 375. So this is not a linear relation. Okay, I want you to pause the video and see if you can decide which of these or both are linear relations. Okay, hope you had a chance to try this one. Well, in this first example, time and number of bacteria. The time is a constant change of 20, but the number of bacteria is a change of +1, +2, +4, so this is not a linear relation. The relation between amount of goods and service tax charged in dollars, so this is the amount of goods. This is a constant change of +60. Here I get a constant change of +3, so this one would be considered a linear relation. All right, this is just another definition, reviewing the definition of a linear relation. A constant change in the independent variable results in a constant change in the dependent variable. So the graph of a linear relation, again, we have our independent variable on the bottom, our dependent variable cost on the top, and this is the car rental. Okay, so if we look from dot to dot, going horizontally, that would be the change in the independent variable, and going vertically would be the change in the dependent variable. And notice each one of these has a change in the independent variable of 20, a change in the dependent variable, of 100 in the independent, 20 in the dependent. For a linear relation, we can calculate the rate of change. And the rate of change is basically the change in the dependent variable, so the change in the y value divided by the change in the independent variable, which is the change in the x value. And this is commonly referred to as the slope. So slope is really rise over run, or mathematically, it's the y coordinate of 0.2 minus the y coordinate of 0.1, which is really my change in y. Divided by my x coordinate of 0.2 minus my x coordinate of 0.1, which is really my change in x. So we want to determine the rate of change for each of these linear relations. And we determined earlier that both of these were linear relations. So my change in my x is +5. The change in the y was +9. So my rate of change for my first one would be 9/5. In my next example, my change in the x direction is 60, and the change in the y is +30. So my rate of change would be 3/60, which could be reduced to 1/20. Okay, that's the first part of section 5.6, properties of linear relations. So give those questions a try, and if you have any questions, check the answers on the website.